You know that feeling when you're diving into a massive, unfamiliar code base late at night?
Oh, yeah. Dark mode on, caffeine injected.
Exactly. Your terminal is glowing, and you're like tracing through thousands of lines of code trying to find the actual engine. And you keep seeing this one flashy API getting called everywhere.
Getting all the glory in the documentation, right?
Right. But then, buried a few layers down, you stumble across this completely different function. It's massive. It's incredibly dense. And you suddenly realize, oh, wow, this is the thing doing all the actual heavy computational listing.
It's the silent workhorse of the whole system.
Yeah.
You spend all your time reading about the interface, only to discover the backend database is where the real magic happens.
Yeah, and that is the exact experience we are going through today. Welcome to the Deep Dive.
Glad to be here.
So for all of you software engineers and developers listening who really want to understand the actual engine under the hood of large language models, we've got a stack of fascinating research in front of us.
We really do. It completely flips how you think about these models.
It totally does. Today's mission is entirely focused on the position-wise feed-forward network, or, the FFN. Because in the AI world, self-attention gets all the celebrity press, right?
Oh, for sure. Attention is on all the magazine covers.
Yeah, but the sources we're unpacking today reveal this massive overlooked giant sitting right next to attention in literally every single transformer block.
Yeah, because attention and the FFN, they play fundamentally different, but, symbiotic roles. Attention is the mechanism that routes the information.
Right.
But the FFN is the mechanism that actually stores and processes it.
And the central, mind-bending concept we're going to explore today is this. What if this dense mathematical network isn't just processing data? What if it's actually operating as a massive, hard-coded, key-value database of human knowledge?
Which is a wild thought.
Yeah.
But to even begin grasping why the FFN might be operating as a database, we really have to look at its physical scale within the architecture.
Yeah, we're talking about an enormous footprint here.
Huge. The contrast is wild. The sources frame this using a CEO versus the employees dynamic.
I love that analogy.
Right. So self-attention is the CEO. It's novel. It's what makes the transformer architecture so groundbreaking. And, it's the face of the company doing the high-level synthesis.
Synthesizing the context.
Exactly. But the FFN, that is the thousands of employees in the warehouse doing the actual data processing row by row.
Let's ground that analogy in the actual parameter map, just for the devs listening.
Yeah, let's do it. If we look at a single transformer block, right, for a model with a hidden dimension size, which we'll just call D.
Okay, detail.
The self-attention mechanism relies on 4 main weight matrices. You've got queries, keys, values, and an output projection.
Standard attention stuff.
Right. And each of those matrices is size D by D. So mathematically, that gives us 4 squared parameters for the attention layer.
Okay, let me put some concrete numbers to that. Let's say our hidden dimension, D, is exactly 1,000. So our token is represented by a vector of 1,000 numbers.
Yeah.
4D squared means we have 4 matrices, each 1,000 by 1,000. That's, 1 million parameters per matrix?
Exactly, giving us 4 million parameters total for the attention mechanism in this block.
Got it.
Now, compare that to the FFN. It only has 2 primary weight matrices, but it fundamentally alters the dimensionality of the data passing through it.
It glows it up.
It really does. The first matrix expands the hidden dimension to 4 times the model size, so its shape is D by 4D.
Wow.
And then the second matrix projects that expanded representation back down from 4D back to D.
Okay, so doing the math on our hypothetical dimension of 1,000, that first matrix is 1,000 by 4,000.
Right.
So that's 4 million parameters just for matrix 1. And the second matrix shrinks it back down. So it's 4,000 by 1,000. Another 4 million parameters.
You got it.
Add them up, and the FFN takes 8 million parameters.
Which means the FFN has 8 aid squared parameters compared to attention's forward squared.
Wait, so it's literally double?
Literally twice as many parameters as the attention mechanism. It accounts for 2/3 of the model's total parameter count.
2/3. That is insane. The sources make this incredibly visceral by pointing to GPT-3.
Oh yeah, the GPT-3 example is perfect.
Right, so that model famously has 175 billion parameters. Out of those 175 billion, roughly 117 billion parameters live purely inside the feedforward networks.
Exactly. When we talk about the staggering size of modern LLMs, we're really, we're mostly just talking about the size of their FFN layers.
So the structure driving that massive size relies on this very specific flow, right? Expand, transform, contract.
Yes. The network expands the token representation into that 4 times larger space, applies a nonlinear activation function, and then compresses it back down.
The researchers use this brilliant analogy of breathing to describe the process.
I think it's the best way to visualize it, honestly.
Yeah, visualizing it as breathing makes perfect sense to me. Like the network inhales, expanding the token's representation into this massive high-dimensional workspace.
Because by projecting the data into a larger space, the model suddenly has the working memory to untangle highly complex overlapping features.
Right. It's exactly like unzipping a compressed file into RAM so your specialized worker threads can examine every single byte.
That's a great way to put it.
And then it exhales. It compresses all the resulting insights back down into the residual stream.
And we should probably define that residual stream for clarity.
Oh, yeah, good call.
You can think of it as the main memory bus or the central highway running through the entire neural network.
The system bus.
Right. Every layer, whether it's attention or the FFN, reads from the central highway, performs its specific computation, and then adds its results back onto the highway before passing it to the next layer.
Okay, so we have this massive breathing giant taking up 2/3 of our server racks,
Yeah.
constantly reading from and writing to the system bus. The natural question is, like, how is this giant actually processing the text compared to the attention layer?
Well, it relies on a property called position-wise independence.
Meaning,
Meaning the FFN applies the exact same mathematical weights, the exact same universal function, to every single token in the sequence. But it does so entirely in isolation.
wait, so token 1 and token 50 pass through the exact same mathematical meat grinder, but they don't interact at all while they're inside?
Right, not at all. Zero interaction. If you think about attention as a group discussion,
Okay.
like all the tokens are in a conference room sharing context, looking around to figure out what a pronoun like it or they refers to.
Right, figuring out the grammar.
Exactly. If attention is the conference room, then the FFN is the private office. After the meeting concludes, every token walks into its own private office, shuts the door, and independently processes the information it just gathered.
See, putting my software engineer hat on, that feels really counterintuitive for a language model. Well, language is nothing but context, right? If token 50 is sitting in an isolated silo, isn't that defeating the entire purpose of the transformer architecture? Like, we want the tokens talking to each other.
It's a fair point, and that tension really highlights the elegant division of labor in the design.
Okay, I'm listening.
You're entirely correct that context is everything. But the context has already been mixed into the token's representation by the preceding attention layer.
Oh, right.
Yeah, attention handles the contextual reasoning and the dynamic routing. The FFN handles the static per-token computation. It's a strict separation of concerns.
Ah, okay. So by the time the token vector gets to its private office in the FFN, its internal state already contains the summary of the conference room meeting.
Exactly. It already knows who it is and how it relates to the words around it.
Okay, so now that the token is sitting in that office, isolated, with this massive expanded workspace and like 117 billion parameters at its disposal, what is it actually doing in there?
And this brings us to the core revelation of the research we're analyzing today. This changes everything about how we view neural networks.
It really does. Because if the FFN is just processing tokens independently, it must be using all those parameters for something foundational.
Right. And we turn to this incredible 2021 research by Morgeva and her colleagues.
Yeah.
They discovered that the FFN actually operates as a factual key-value memory store.
A key value store, which, translating that into developer terms, it's basically a massive fuzzy hash map or dictionary baked directly into the neural weights.
Yep, it transforms the FFN from a generic mathematical transformation into a learned database.
That is so cool. So the first linear layer, W1, acts as the keys, right?
Correct. It holds a vast set of patterns the network is trying to match against the incoming token vector.
And then the second linear layer, W2, serves as the values.
Exactly. That represents the actual factual information retrieved when one of those keys registers a map.
So a token comes down the residual stream. W1 checks it against thousands of stored keys.
Yeah.
If it finds a match,
Say, a geometric pattern in the vector that represents the concept capital of France.
right. If it finds that, it triggers the corresponding value in W2.
And then W2 injects the mathematical representation of Paris directly into the token's vector.
That is wild. So the model isn't reasoning about Paris in some abstract cognitive way. It's literally just executing a highly complex differentiable database lookup.
Exactly. And Mordiva's team proved this was happening through extensive ablation studies.
They didn't just guess.
No, they treated the network like a code base and started hunting for specific variables. They monitored the activations when feeding the model prompts about facts, like the Eiffel Tower.
Okay.
And once they identified which specific neurons in that expanded workspace were spiking, they surgically disabled them.
That's like intentionally introducing a bug into a specific sector of a database just to see which web page goes down.
That is the exact methodology. They zeroed out the specific W1 and W2 weights tied to the Eiffel Tower being in Paris.
And what happened?
When they ran the model again, it suddenly had absolutely no idea where the Eiffel Tower was located.
Wow.
But here's the crazy part. It didn't break its understanding of English grammar, and it didn't forget the locations of other monuments. It just lost that single, highly specific row in its database.
So the knowledge is physically localized in those specific weights.
Yes.
But, okay, for a key value lookup to function in a piece of software, you need a mechanism to decide which keys actually matched the input.
Right.
Because in a standard Python dictionary, it's a strict hash collision. In a neural network, it's fuzzy math based on vector similarities.
Yeah.
Something has to act as the filter.
And that filter is the activation function. It's the mathematical operation sandwiched entirely between the W1 key matrix and the W2 value matrix.
And tracing the evolution of these activation functions is like a masterclass in systems optimization. It started with ReLU, right? The rectified linear unit.
Yeah, ReLU is about as simple as an algorithm gets. If the incoming number is positive, it passes it through unmodified. If the number is negative, it outputs a hard 0.
Which is really fast to compute, but it comes with a fatal flaw for a database. Dying neurons.
Oh yeah, the dying neuron problem.
Because of that hard cutoff at 0, if a neuron's value consistently falls into the negative range, it outputs 0. During backpropagation, the gradient of 0 is 0. The chain rule just stops dead in its tracks.
Yep, that specific weight can never update or learn again.
You essentially end up with permanently dead sectors on your hard drive.
Which is terrible for capacity. So, to fix this, the industry moved to GLU, the Gaussian error linear unit. This became the standard for models like BERT and GPT-3.
How does GLU fix it?
Well, GLU replaces that hard, sharp angle at 0 with a smooth, continuous mathematical curve.
Ah, so large positive values pass through normally, large negatives get squashed very close to 0, but right around the 0 mark, the curve is completely smooth.
Exactly. Because there's no sharp cutoff, the gradients can always flow. The backpropagation never hits a brick wall, which keeps the entire database healthy and tunable.
That's so elegant.
It is. Researchers also experimented with SciOU, or Swish, which operates on a very similar smooth curve to GLU, but can be, slightly more efficient to compute depending on the hardware.
But if we look at the state-of-the-art open-source heavyweights today, models like Llama and Mistral, they've abandoned GLU entirely.
They have. They moved to SwishGLU, Swish-gated linear unit. And SwishGLU doesn't just swap out the math equation, it fundamentally rewrites the architecture of the FFN itself.
How so?
Well, earlier we established the FFN relies on two matrices, right? W1 for keys and W2 for values.
Right.
SwishGLU introduces a third matrix.
Wait, what?
Yeah, the architecture is split into W-gate, WUP, and wood down, with way down serving the same role as the old W2 value matrix.
Okay, as a developer, the moment you say third matrix, alarm bells go off regarding the parameter budget.
Of course.
Like, we already established this FFN giant consumes 2/3 of the model's memory. If we arbitrarily add another massive matrix to every single transformer block, our VRAM requirements would skyrocket.
And the designers anticipated that exact hardware constraint.
Okay, so how did they fix it?
To keep the parameter costs flat while adding a third matrix, they simply reduced the size of the expanded hidden dimension.
Oh.
Yeah. Instead of expanding the token's workspace by a factor of 4, they expand it by a factor of roughly 2.67, specifically 8/3 D.
That is so clever. So they shrink the width of all the matrices just enough to afford the memory footprint of the third matrix.
Exactly. The total parameter count stays exactly the same, but the internal architecture is completely different.
But why?
Yeah.
Like, why go through all that complex reshaping just to split the first matrix into two?
Because it splits the database lookup into two distinct specialized pathways.
Okay.
The gate pathway is responsible for deciding which dimensions should be activated. The up pathway provides the actual raw values.
I see.
And then once both pathways process the input, their outputs are multiplied together element-wise.
The sources use a fantastic analogy for this element-wise multiplication. They compare it to a recording studio mixing board.
Yes, it perfectly describes the math.
Right, so the up pathway is the raw audio signal coming directly from the instruments.
Yeah.
It's generating all the possible sound values. But the gate pathway is the producer sitting at the mixing board.
Yep.
The gate controls the faders, sliding them up and down, deciding exactly how much of each specific instrument actually makes it into the final master track.
And multiplying them together creates a highly refined selective retrieval system.
Instead of just a binary yes or no.
Exactly. Instead of a binary yes or no on whether a fact is relevant, the model can dynamically dictate exactly how much of a specific factual nuance should be blended into the token's representation based on the context.
It acts as an internal attention mechanism specifically for filtering noise out of the database.
That's exactly what it is.
So we're looking at a beautifully optimized, dynamically gated, massive key-value database taking up the vast majority of an LLM.
Yes, we are.
And when we zoom out and connect this architectural reality to the behavior we see in AI every day, so many mysteries start to make sense.
Oh, absolutely. The FFN as memory framework perfectly explains the scaling laws that have dominated AI development.
Like how bigger is always better.
Right. We've observed for years that simply building larger models results in systems that know more world trivia. Well, a larger FFN literally equates to a larger hard drive.
You're just adding more rows to the key-value database.
Precisely. It also demystifies model editing.
Oh, right.
Because if factual knowledge isn't distributed ethereally throughout the entire network, but is actually localized in specific weights, developers can go in and overwrite them.
You can surgically tweak a specific cluster of weights and force the model to genuinely output that Lyon is the capital of France without having to spend millions of dollars retraining the entire system.
Exactly. But I think the most practical implication of this framework, however, is how it reframes our understanding of AI hallucination.
Oh, man. This is my favorite part. If the FFN is a key value store, a hallucination is not the AI lying or deciding to be creative.
Nope.
It's simply a fuzzy hash collision. It's a poorly executed database retrieval.
It's an indexing error.
Yeah. Imagine walking into an absolutely massive library and asking the librarian for a highly obscure book. The librarian, who is playing the role of the FFN here, scans the millions of shelves. They find a pattern that closely resembles your request, and they hand you a book. The title sounds incredibly plausible. The author's name matches the domain. But because the vector match was only approximate, the actual content of the book is completely wrong.
The activation function crossed the threshold, the weights delivered a value, but the retrieval was an approximation rather than an exact match.
And running 117 billion parameters through matrix multiplication for every single word generated is incredibly computationally expensive.
Oh, very.
Since we know the FFN is just a massive database, how are engineers optimizing it to make these models cheaper to run in production?
Well, the bleeding edge of parameter efficiency is entirely focused on the FFN layer.
Makes sense, since it's the biggest part.
Right. And the most prominent technique deployed today is the mixture of experts, or MOE architecture.
This is the underlying architecture for models like Mixtral and reportedly GPT-4, right?
That's the rumor, yeah. And rather than building one monolithic, gigantic FFN that fires every single parameter for every single token, MOE breaks that massive database up into several smaller specialized expert FFNs.
Oh, nice.
And crucially, it introduces a router mechanism.
Which acts exactly like a load balancer in a microservices architecture.
Tell me more about that.
Well, when a token enters the FFN layer, the router analyzes it and says, this token is highly relevant to Python code. I'm not going to spin up the entire 117 billion parameter database.
Right.
I'm only going to route this payload to expert number 3 and expert number 7, which specialize in syntax.
Exactly. The model retains the massive total storage capacity of all the experts combined, but during inference for any given request, you are only paying the computational cost to activate a small fraction of them.
That is brilliant. And engineers are continually pushing these optimizations further, right?
Oh, yeah. We're seeing research into sparse FFNs, where the system attempts to predict ahead of time which neurons are going to output 0 anyway due to the activation function.
Oh, so it just skips them.
Yeah, it simply skips the math for those neurons entirely.
That saves so much time.
And there's also significant progress in low-rank factorization.
What's that?
This involves taking one of these mathematically dense, massive matrices, like a 4,000 by 4,000 matrix, and decomposing it into two much thinner matrices multiplied together.
Okay.
It drastically reduces the VRAM required to store the database while attempting to maintain the same relational patterns.
So the entire field of LLM optimization is fundamentally just a quest to make the FFN database more efficient.
Pretty much.
Let's bring all of these concepts together. We started this deep dive tracing the code base, looking for the real engine under the hood.
Yeah, we found it.
We found the position-wise feed-forward network, an overlooked giant taking up 2/3 of the model's parameters, quietly inhaling data into a massive workspace and exhaling insights back to the system bus.
And we examined how it isolates each token in its own private office to process information independently of the sequence.
Right, and we unpacked the research, proving it operates as a learned key-value database, a fuzzy hash map storing human knowledge in W1 keys and W2 values.
And we traced the brilliant systems engineering of Pine SWGLU using that mixing board approach to dynamically gate retrieval without blowing up the parameter budget.
The FFN really represents this incredible intersection of abstract mathematics and highly pragmatic systems engineering.
It really does.
It
Fascinating.
fundamentally changes how we interact with these systems. And it leaves me with a final provocative thought for everyone listening to ponder.
Oh, let's hear it.
You're sitting at your terminal analyzing the architecture of these models. If 2/3 of a large language model is essentially a learned database of facts,
Yeah.
and if researchers have already proven they can map specific neurons to specific concepts through ablation studies,
Yeah.
how long until we stop training models on billions of random internet documents?
Wait, you're asking when we shift from training a neural network to directly populating a database?
Exactly. How long until we develop the tooling to just directly program facts into the weights, exactly like we insert rows into a traditional SQL database?
That is a wild thought.
If we know where the database lives and how it's formatted, the next logical step in software engineering is building the API to write to it directly.
It's only a matter of time.
Right. Well, thanks for joining us on this deep dive. Keep hacking, keep exploring the code base, and we will catch you on the next one.